Okay, so this is another example problem. This is example 3. The issue with this problem is it's a fancy problem, not a shift register problem. But we need to look at this problem and just, first of all, decide what we need to do with this thing. So what this is doing, this problem is doing, is I press a button and I'm going to start accumulating values. And essentially, I'm going to grab one value per clock cycle and accumulate it. And I'm going to keep doing that until one of those values exceeds the 8-bit range. Okay, once it exceeds the 8-bit range, I'm going to keep displaying that output and then transition back and wait for another button press. So the thing to notice in the circuit is it's accumulating, so it needs an accumulator, which means I need a register and a ripple carry adder. That's my accumulator. And so what else is this problem doing? That's about all the hardware it needs other than a state machine to control it. So the hardware is going to be accumulator and a state machine. And the fun stuff happens when fun stuff happens with the associated timing diagram, which is coming up after this problem. Okay, so the very first thing to do in this problem, as with all problems, is get a handle on what the black box diagram is going to be. So I have a circuit sitting there. The output's 8 bits. I'm going to call that sum. I have an 8-bit input, which I'm going to call val. I have it's clocked. And I have a button to start this thing off. And I think that's all I need to do in this problem. Okay, so the circuitry here, we agree that this is accumulating numbers, so I need an accumulator. So first thing I'm going to do is I'm going to come up here and draw an accumulator. There's a register. There is, I think I'm going to erase that. There is a ripple carry adder, and I'm going to connect this accordingly. A B. The B input, remember I'm adding that val input, so one of the inputs to this ripple carry adder is going to be the current running total, which is coming out of the register, which is this guy here, and this is going to be sum. The other input to ripple carry adder is the input from the outside world. Okay, so the sum is going to go over to the data input on this register. This is the clock circuit, and I know I'm going to be loading values onto this, so I need a load input on that thing. And looking good. Okay, so anytime I'm accumulating values, I need to start the accumulator at 0. I mean, it makes no sense to start accumulating from something other than 0. So by all means, I need control of this thing. So practically every time I use an accumulator, I have the ability to clear the accumulator. So I'm going to put that in there. And lastly here, looking good, I need some way to stop accumulating. Okay, so the problem is clearly states that I'm going to stop accumulating when the value that I potentially will add will cause a carry out of this thing. Essentially, the carry out is going to carry out of the 8 bits. So if the value I'm adding is going to carry out of the 8-bit number, the carry out is going to be asserted. Okay, so looking good here. As it is, I've got carry out's going to be a FSM here. I certainly need FSM. Carry out is a status input, so that's going to be an input to the FSM. FSM is clocked. The control outputs of this FSM are, if you look at this thing, are going to be the control inputs of that register, which is clear and what's the other one? Load. Okay, looking good. I think that's it. I'm ready to draw the state diagram. Okay, so if we look at this thing, I'm going to have many ways to do this. I, of course, need a button input on this thing, too. Many ways to do this. I like doing it as a Mealy machine. It saves a state. I think it's clear. So I'm going to draw a state here. I'm going to call it the wait state. And what it's waiting for is a button press. Okay, so if it gets that button press, it's going to go do something else, which I'm going to call the accumulate state. Okay, so this is because I've made this into a Mealy machine. In this wait state here, I need to account for both the clear and the load. And so what's important here, because it's a Mealy machine, so long as no one's pressing that button, I'm not going to clear that register. But the second someone presses that button, I want to clear that register. Okay, so I've handled one of the control outputs there. I need to handle the other one, which is load. So while I'm in that load state, I want that output persistent. So what I need to do is specify that the load is turned off. And that looks good. I think I've covered everything. So the carry out input to the state machine, I don't really care about it in this initial wait state. So essentially it's a don't care. I could have put it down there, but it's don't care. It messes up the diagram. I don't put it in there. Okay, so I'm coming over to this accumulate state, and that's where I'm going to do my accumulation. So one thing I can do right away is while I'm accumulating, I certainly don't want to clear the register, so I'm going to turn the clear off. So I have two options in this accumulate state. So if the current value on the ripple carry adder does not generate a carry out, that's when I want to add. So no carry out, I want to add. And so essentially what I'm doing is no carry out, I'm going to load that added value into the register. We can put an 8 on that one. The other issue here is if I do generate a carry out, what I want to do is transition back to the beginning and make sure I do not load a new value into that. So essentially the current values on the ripple carry adder cause there to be a carry out. I don't want to load that value into that register, so I'm technically displaying on the sum output is the result of the last addition. And okay, so that's it for this register. What I want to do here is grab this diagram and work state diagram and work out a timing diagram, which I will try to figure out right now. Okay, so what I've done is included a timing diagram on this. Okay, I've included the timing diagram, and I'm going to fill it in. So this is not the easiest stuff in the world. This is really, every time I look at these, I have no idea what to do, but I always just work through it and crank through it and eventually arrive at the right answer. So don't let these defeat you. Just do what you need to do on these things. So I'm going to look at this thing and look for some starting point. And so the starting point I'm going to look at is, I guess I'm going to look at this state transition here. So the state transition from this state is based on the fact that button equals 0. So when button equals 0, it transitions back to the wait state. So I can put like I said, I can put a wait state there. Okay, so it transitions to the wait state. Okay, but also, if you look at this button and clear input, you can see that the clear input is always going to be the same as the button input when I'm in the wait state. Okay, so that means it's going to look like this. Once that button goes high, I'm going to, the clear is going to go high. Okay, so I'm going to say, I'm going to put a fatter line on this thing. Okay. So the issue on this is that I forgot to say, and that's okay, I'm going to say async for the clear. Okay, so the clear is asynchronous. So that means the second the clear turns on, the sum is going to go to 0. So here's the sum right here. And I'm going to say, the second that goes on, it clears to 0. And as a result of this clear going on. Okay, I'm looking good on this thing, and so we'll do some other stuff here. Let's look at carryout. Carryout, at this very moment, the carryout is based on the fact that there's an FF and a 4-7 on the input of the RCA. That's going to overflow this thing. So in this state, the carryout is going to be not a 0. The carryout is going to be a 1. Okay, and it's going to stay a 1. It's a combinatorial circuit until one of those inputs to go to 0, and the carryout goes to 0 right when that other input, or right when the register gets cleared. Okay, so that register gets cleared. The other input to RCA is going to go to 0. The carryout is going to turn off. Okay, so what else do we got here? Wait. Okay, here I'm in the button state. Button's a 1, so I'm going to the accumulate state. So I'm going to put that down. Looking good. And looking good. So what else can I do on this thing? Well, let's do the load. Notice that anytime I'm in the wait state, the load is turned off. So I'm going to indicate that right there. So looks like I've got these first two states done, and let's see what else I can do there. Okay, let's check this out. Take it bit by bit. In the accumulate state, the clear is off, so this thing goes off, and it stays off. Okay, and what else is true in the accumulate state? In the accumulate state, because the carry out is a 0, right here, the load is going to be a 1. So right after I get into that state, the load is going to turn on, and the carryout's not going to change because nothing's going to happen until the next clock edge when it latches that output RCA into the register. And so we're looking good here. So this thing is continuous also. I don't need to do that. And so what's interesting at this next clock cycle, I have FF on the B input of the RCA, and I have 0 on the A input of the RCA. Those are going to be added up and latched into the register. So the register value at this clock edge, due to the fact that that load down here is asserted, is going to load FF into the counter, FF. Okay, that's looking good. I'm in the accumulate state. At that point, the carryout is 0, so I'm going to go back to the accumulate state. Okay, looking good. So after I get into this state here, this second accumulate state, I have an FF on one input and an FF on the other input. That's going to make this carryout turn on. And here I have an FF and a 0, 1. That's going to be still generate a carryout. And looking good on that thing. And so if you notice that when the carryout in the accumulate state is a 1, the load becomes a 0. Okay, and clear. I'm in the accumulate state, so the clear is turned off. That looks good. Load's turned off. But the carryout's turned on. So the carryout's turned on in this second accumulate state. So after that, I'm going to transition to the wait state, and it is going to stay there because I can tell the button's not pressed. Okay, so and so the clear is always going to be off because no one presses the button. The wait state, the load, it's not going to load the new value. The load is always off in the wait state. So we're almost done here. The output, it didn't load a new value. Nothing's going to cause it to load, so I'm done with that. The last thing I need to do is this carryout. So this carryout is always going to be asserted because I always have an FF for one of the inputs, and this changed to 0, 1. 0, 1 plus FF is still going to generate a carryout. Okay, so there it is, clonking through this thing. Generally speaking, these are, there's three aspects to these problems. Is one, the circuit, two, the state diagram, and then there's the timing diagram, which is kind of a interesting interplay between the state diagram and the circuit. Not simple to understand, but I guarantee the more you work with it, the better you'll understand these circuits, and you definitely won't regret it.